Hello everyone, and welcome back to this series on single variable calculus. Today we're going to be continuing our exploration of different integration techniques and continuation of u-substitution of integration by parts, and introduce another method that can give you access to finding elementary representations for a wide class of functions, and that is partial fraction decomposition. So, the golden question that we plan to answer today is starting as follows. Suppose that p and q are polynomial functions. Can we always find elementary antiderivatives for the integral of p of x divided by q of x with respect to x? And when I say elementary derivatives, I mean, can you represent the answer to this question in terms of finite sums of polynomials, logs, sines, cosines, tangents, inverse tangents, inverse sines and cosines, and the sorts, right? Or combinations, products, and quotients of each, right? So, can we do this? The answer, of course, is yes. But I'm not saying that it's easy, but using partial fraction decomposition, integrals of quotients of polynomials always has a closed form representation. So let's first off go ahead and state one of the theorems that allows us to be so certain of this result, and that's the fundamental theorem of algebra. Some people will just abbreviate it as FT. And it says the following. So suppose that the degree of polynomial p is equal to n, and keep in mind n must be a natural number. Then there exists n complex numbers. Let's call them ak, and of course they're going to belong to C. Now, I want to say before I finish this statement, finding these numbers is not always that easy, and sometimes numerical methods are necessary. But if you can find these numbers ak, a1, a2, a3, a4 down to an, then you can write this polynomial p as follows. P of x is going to be equal to b times the product from k is equal to 1 to m of x minus ak for some number b not equal to 0. And some people will call b the leading coefficient of p. Right? So this is going to give you some insights as to why we can always find elementary representations for quotients of polynomials p of x over q of x, right? And I'll go through a couple examples to sort of give you some idea as to how you could actually prove that. So what I want to do is start off with a few examples of antiderivatives that you should be able to do using the methods that you already know. So let's assume that we have the integral of dx divided by ax plus b, and of course let's assume that a is not equal to 0. So you should be able to quickly identify this antiderivative just by observation, or you can use u-substitution by letting u be equal to ax plus b, differentiating it, isolating your dx differential, read in terms of u and du, and then resubstitute back. But you should be able to quickly observe that we have the integral of 1 over a linear function. And always, when you have the integral of the reciprocal of a linear function, you can always represent it in terms of a natural logarithm. In particular, you can write this as 1 over a times the natural log of ax plus b plus some arbitrary constant c. And in case you aren't convinced of that, you can always differentiate that and go backwards, and you should be able to verify that that is indeed the case, right? But that's a very easy problem, so let's of course go ahead and make it just a tad bit more difficult. Instead of a linear function being on bottom, I'm also going to put another linear function on bottom, and I'm going to put another linear function on top. So 5x plus 2 over 3x plus 7 with respect to x, right? So how am I going to differentiate or integrate this? Now there are several ways you could tackle this problem, but what I actually want to do is use long division on this, right? Because what we have here is a degree 1 divided by a degree 1, whereas for the example before we had a degree 0 divided by a degree 1. So the degrees of the top and bottom match, so you should be able to use long division to represent the quotient of polynomials in a different way. So let's recall how we're going to do long division. So the bottom is going to be 3x plus 7, and we want to divide that into 5x plus 2. Okay, so we need to ask ourselves the question, what do we have to multiply 3 by to get 5? And the obvious answer to that is obviously going to be equal to 5 over 3. Okay, so then we're going to take 5 over 3 and we're going to multiply it by 3x and 7, and then we're going to get some object that we're going to subtract from 5x plus 2, and that's going to give us hopefully a remainder term. So what is 5 thirds times 3? Well, 5 times 3 is 15, and 15 divided by 3 is going to be 5, so 5 thirds times 3 is going to be 5. And 5 thirds times 7 is going to be what? So 5 times 7 is 35, and then we're going to divide that by 3, so 35 over 3. So we have 5x minus 5x, and they obviously will cancel each other out. And then we're going to have 2 minus 25 over 3. And once you get a common denominator, you should be able to get what? So multiply that by 3, and then we're going to have 3 times 2 on top. So we're going to have 6 minus 25, and that's going to give you some particular number, and you should be able to verify that that's going to be minus 29 thirds, unless my basic math is slightly off today, which is always a possibility. Right? So that's going to be our remainder term, and 5 thirds is going to be our quotient. So what is this going to come out to? So this is going to be equal to the quotient, which is going to be 5 thirds, plus the remainder, which is minus 29 over 3, divided by the divisor, which is going to be 3x plus 7. So that's just a basic representation of this particular quotient in terms of long division. Okay, so what do we have here? And keep in mind, this is integrated with respect to dx. So now what do we have? So we have the integral of a constant, that's just a linear function. We have the integral of a degree 0 over degree 1, that's just a natural logarithm, just like we said before. So we can represent this in terms of an elementary antiderivative. And what is that going to be? So that's going to be equal to 5 thirds x, and then we're going to have what? We're going to have minus 29 over 3 times, now we need to take that 3 and reciprocate it, so 1 over 3 times the natural log of that denominator 3x plus 7 plus some arbitrary constant c. We obviously can simplify that product of fractions and write it in a neater way, so that's going to be just 5 thirds x minus 29 over 9 times the natural log of 3x plus 7 plus c, and that would be your answer for the original problem. And that's at least one way to tackle it. All right? So now let us just take one more example, slightly more complicated of course, but maybe you can try this on your own. Let's assume that we have the integral of x squared plus 7x plus 3 all over x minus 4, and let's assume that we want to integrate as usual with respect to x. Right? You might want to pause this video and try this on your own. So what do we have? So we're going to be using long division again, so we're going to be dividing x minus 4 into x squared plus 7x plus 3. So what do we have to multiply x by to get x squared? That's obviously going to be x, and then we're going to multiply x by that divisor. So that's going to give us x squared minus 4x, and then we subtract. I always want to put that parentheses there just to remind myself that you have to distribute that negative sign. So we have what? So x squared minus x squared, that's 0. 7 minus negative 4, that's 7 plus 4. That's going to be equal to 11x, and then we bring down this 3 and repeat. So what do I have to multiply x by to get 11x? That's obviously going to be 11. And 11 times x, that's going to be 11x. And 11 times negative 4, that's going to be minus 44. Subtract parenthesis. And then we have 3 minus negative 44. That's the same as 3 plus 44. That's going to be 47. That's our remainder. All right, with our divisor, x plus 11. So let's rewrite this in our quotient form. So that's going to be what? So that's going to be the integral of x plus 11. That's our quotient. And then we have our remainder, 47, all over divisor, x minus 4. All right? So integrate as usual. So we have the integral of a linear function. That's just going to be a quadratic function. So that's just going to be equal to 1/2 x squared plus 11x. And then we have over here 47 times the natural log of x minus 4 plus our arbitrary constant c. And that is our elementary antiderivative. right? So what is the beautiful trick for these? Long division is definitely your best friend. In particular, when the denominator or the numerator polynomial has a higher degree than the top. So long division is definitely a very good tool when the degree of p is greater than or equal to the degree of q. In particular, the top has a larger degree than the bottom, right? But in all of these examples, I've only been considering the case where the degree of the bottom, in this case, is equal to 1. But what happens when the degree of the denominator is more than 1? That's where our new method is going to come into play. So now let us consider the case where the denominator of our rational integrand is quadratic or higher. We're obviously going to start off with quadratic just to show sort of how to partial fraction decompose this integrand. But generally speaking, what you would want to do is figure out how can we factor this polynomial. Now, this particular case is actually quite easy because there does exist two integers that multiply to give you 10 and add together to give you minus 7. So we can actually write this as the integral of dx all over x minus 2 and x minus 5. Right? So that's quite easy. Now, just because you can factor all polynomials doesn't mean that they factor nicely. But they do factor nonetheless, so you'll always be able to theoretically find these numbers 2 and 5. And in case you're not interested in those particular two values, you can always call them a and b temporarily, and so you can either analytically find them or numerically approximate them. Now, the next thing that we need to do is use a method known as partial fraction decomposition. So what does that mean? So we're going to take our integrand, 1 over x minus 2 and x minus 5, and decompose this into partial fractions. Hence the name, partial fraction decomposition. The first fraction is going to be something over x minus 2 plus something else over x minus 5. And we just need to figure out what those somethings are equal to. Okay, so if I take this algebraic problem and I rearrange it, what is that going to give me? So I can multiply both sides of this equation by this denominator and rearrange, and that's going to give me 1 is equal to a times x minus 5 plus b times x minus 2. Now what I want to do here is create a systems of equations and find out what a and b needs to be equal to in order for this equality to hold. So I'm going to choose x is equal to 5 first, and that's going to give us what? So when x is equal to 5, that eliminates, and that's going to give me 1 is equal to b times 5 minus 2. That's going to be equal to 3. So that means b must be equal to 1/3 for this to be true. Similarly, if I let x be equal to 2, that's going to be 1 is equal to 2 minus 5. That's going to be equal to minus 3. A, and then 2 minus 2 is going to be equal to 0. So that means a must be equal to minus 1/3. Right? Once we have our a, negative 1/3, our b, our positive 1/3, now we go back to our integrand. So that means this is going to be equal to the integral of a all over x minus 2 plus b all over x minus 5. And then use partial fraction decomposition to figure out what a and b should be equal to. But if you don't really care about what those a's and b's are equal to, you still can technically look at this and be like, oh, those are two natural logs together, just added to one another, right? So we actually know what our a and b are, so we can actually finish this problem and write this as what? So that's going to be minus 1/3 times the natural log of x minus 2. And some people use absolute values for the input of natural log, and that would be perfectly fine. Depends on the domain you're interested in. And then plus positive 1/3 times the natural log of x minus 5 plus our arbitrary constant c, and that would be your final answer, right? So that actually comes out to be very, very nice. So let's actually look at another integral problem that has our, let's just call this example 5. And this actually has a nice answer. You probably already know it. 1 over x squared plus 1 dx, right? Pause this video if you want for a moment and tell me what you think the answer is. But you should actually already know that this is equal to arctangent of x plus c. Right? So is this really a special case of partial fraction decomposition? Actually, no. This is just a special way of writing our partial fraction decomposition problem, right? So let's actually explore that out a little bit and sort of see what's going on here, because this is a quotient of two polynomials p and q, but here our denominator is quadratic. Now, there is a theorem from Fundamentals of Math, and it says the following, and there are some courses that go into this a little bit more deeply, but if I is equal to the square root of -1, then we can actually rewrite sine as the following: 1 over 2i times e to the ix minus e to the minus ix, and you can also write cosine in a similar way. Cosine is 1 over 2 times e to the ix plus e to the minus ix. So those are complex exponential representations of that. And you can also write tangent as the quotient of those two, and that's just going to be equal to 1 over I times e to the 2ix minus 1, and then e to the 2ix plus 1. And I'll leave it as an exercise to show that if this is true and this is true, that it implies that that is true as well. So is it possible that we can solve this integral in a different way using partial fraction decompositions and get our tangent of x, just in case you just didn't know that rule from single variable calculus or differential calculus? So let's actually just call that example 5.2 our second way of solving it. So what do we know? So our goal is to solve the integral of 1 over x squared plus 1 with respect to x. So our first goal is to partial fraction decomposition it. So we need two baby fractions, a over something, b over something, such that they must add to 1 over x squared plus 1. And that's obviously a sum of perfect squares, so you should already know that that is going to factor into x plus I and x minus I. Right? And if you don't remember that, then you know there's just a special form factoring trick from Math Foundations. Right? So we want that fraction to be equal to that fraction, so we just need to figure out what a and b are going to be equal to. So that means 1 must be equal to a times x minus I plus b times x plus I. And now we need to figure out what a and b must be. So if I let x be equal to I, that's going to eliminate that part, and that's going to give us what? 1 is going to be equal to b times I plus I. That's going to be equal to 2i times b. So that means b must be equal to 1 over 2i. And if I let x be equal to minus I, that's going to be equal to 1 is equal to minus 2ia, which means that a must be equal to minus 1 over 2i. There's our a and our b. And as we can clearly see, we have these two natural log expressions. And we should be able to solve this. So this is going to be equal to what? So that's going to be equal to minus 1 over 2i times the natural log of x plus I plus 1 over 2i times the natural log of x minus I plus some arbitrary constant c. And that would be your answer. Now a question for you. Is this the same as arctangent of x plus c? Yes, indeed. And I'll leave that as a very advanced exercise for you to verify on your own. Now let's consider the following problem. The first thing that we need to look at is what makes this problem different from the rest. Well, the first few examples, again, were quotients of rational functions whose denominator was just degree 1, which was just a natural logarithm function. And the last example was, okay, we had two different linear factors multiplied on the bottom, which gave us a quadratic denominator, and then we used partial fraction decomposition. But what we have here is again a quadratic denominator, but we have a repeated, some people will call it a root or intercept or factor. Either one would be perfectly fine depending on context. So the question now is, how can we find this integral? Right? Now, you should actually already know the answer to this integral. A quick u-substitution or an observation can easily verify that this is actually just going to be equal to -1 over x plus 1 plus c without any hesitation, right? But can we still obtain this answer via partial fraction decomposition, or is this, again, a special case? And of course, we know that it shouldn't be a special case, just like our arctangent. But maybe there is some scenic route that we need to do in order to get what we need via that particular method, right? So when you have a integral of this form, where we have a 1 over x plus 1 squared, which is just x plus 1 times x plus 1, if we want to use partial fraction decomposition for this, will it be a over x plus 1 plus b over x plus 1 as well? You should be able to verify that this actually wouldn't make any sense. Because if it is a over x plus 1 plus b over x plus 1, then it's just going to be equal to a plus b over x plus 1, which is just going to be equal to some other number, call it a plus b, all over x plus 1. And that means a quadratic rational and a linear rational are equal up to a scalar value. And that wouldn't make any sense now, would it? Right? So this partial fraction decomposition wouldn't work at all. But one can verify with a little bit of algebra and intuition is that what you actually need is a square on that particular denominator, right? And once you work this out, then it's like, okay, now I can integrate that. That's just a natural logarithm. And then I can just integrate that with a simple u-substitution, right? But since that's pretty much what the original problem is, that is, you're going to find that a is going to be equal to 0 and b is going to be equal to 1 for this particular problem, partial fraction decomposition doesn't really get us anywhere for this particular type of problem. So let's actually take a look at another problem where partial fraction decomposition will be of use to us. So let's consider the integral of 3x plus 5 all over x plus 1, the quantity squared, dx. Now, keep in mind, if the degree of the top is bigger than or equal to the degree of the bottom, then we need to start with long division. So this is pretty much like a strategy for solving integrals of rational functions. If the top has a higher or equal degree than the bottom, then long division will always put it in a smaller over greater form, and then we can use partial fraction decomposition to finish it off. So what we have here is a degree 1 and a degree 2, so long division is not going to be necessary for this particular problem, or this might be a sub-problem where we have like a degree 3 over degree 2. And that's going to give us one of these as our possible sub-integrants. So the first thing that we need to do is figure out, okay, how are we going to partial fraction decomp this particular problem? So our interest is to take 3x plus 5 over x plus 1, the quantity squared. The bottom trivially factors into x plus 1 times x plus 1, so we have a repeated root. So we're going to have some constant over x plus 1 plus some constant over x plus 1, the quantity squared. And of course, if it was x plus 1 to the power of 3, then you would add a third fraction to be like c over x plus 1 cubed, and then work that out. The only issue is the systems of equations is going to be a little bit more annoying to deal with, but nothing that the wise, computationally intensive master couldn't figure it out on their own if they needed, right? So I'm just going to multiply both sides of this equation by x plus 1, the quantity squared, and see where that gives me. So that's going to give us 3x plus 5 is going to be equal to a times x plus 1 plus b times nothing, right? So obviously this is going to be true. This needs to be true for all x. So I'm just going to pick a couple x's that is going to work in our favor to sort of figure out what a and b are going to be equal to each other. So the first value is going to be x is equal to negative 1. So I'm trying to eliminate this particular term. That's going to give us negative 3 plus 5 will be equal to b, which means that b is going to be equal to 2. Right? The other x value is really up to you. I'm going to choose 0 because 0 is just a great number to work with most of the time. But keep in mind this must be true for all x. Right? I'm just choosing 0 to be a particular one. Right? So when x is equal to 0, that's going to give us 5 is equal to a times 1 plus b. So 5 is equal to a plus b, but b is equal to 2. So that means 5 must be equal to a plus 2, which means that a must be equal to 3. Okay? Once we have that, then we can go back to our integral and hopefully solve. Right? So we have the integral of 3x plus 5 all over x plus 1, the quantity squared, dx, will be equal to what? So we have a over x plus 1 plus b all over x plus 1, the quantity squared. Right? So we can directly integrate that. That's just the natural log. And then we can directly u-substitution that or solve it by observation very, very quickly and get our answer as desired. So what is that going to come out to? So that's going to be equal to 3 times the natural log of x plus 1, and then minus 2 times 1 over x plus 1. No power there, plus some arbitrary constant c. I actually don't like writing my 2 there. Let's just write it like that. So that would be your final answer to that very beautiful problem. Right? Now, is there only one way to solve an integral? Actually, no. There's actually a broad community of people who love solving integrals in a variety of different ways and sort of view it as an artistic, an artistic realm. So let me actually take the same integral, 3x plus 5 over x plus 1, the quantity squared dx, and actually show you another way you can actually solve this integral without using partial fraction decomposition. So what I'm actually going to do is I'm going to rewrite this top in terms of an x plus 1 plus some other stuff. Right? So if I have x plus 1 written on the top, what must I add to it to get 3x plus 5? Well, x plus something gives us 3x. That's obviously going to be equal to 2x. And 1 plus something is going to be equal to 5, so that's obviously going to be equal to 4. And then the bottom is just going to be equal to x plus 1 squared. That's not really my focus, aside from me trying to line those up into each other. Right? So that's going to be equal to what? So that's going to be 1 over x plus 1 for that first term. And then over here, what are we going to have? So we're going to have 2x plus 4 all over x plus 1, the quantity squared, dx. So this very first integral we can solve immediately, so that's wonderful. So that's going to be equal to the natural log of x plus 1, and then we're going to have a plus c eventually, so let's just put it there so we don't forget it. And then we're going to have the integral of this object. But keep in mind, I can write 2x plus 4 by factoring out a 2, because that's going to give us 2 times x plus 2. And I can write x plus 2 as x plus 1 plus 1. So I can write this again as x plus 1 all over x plus 1, the quantity squared, dx, right? So once I have that, then I can sort of eliminate one of those x plus 1 squareds, and that's going to give us what? So we're going to have the natural log of x plus 1 plus c plus 2 times what? So that's going to be equal to the integral of 1 over x plus 1 again. And then we're going to have a 1 over x plus 1, the quantity squared, dx, and we know how to deal with that. Don't forget to distribute your 2 there, okay? So we're going to have the natural log of x plus 1 plus c plus 2 times the natural log of x plus 1, and then we're going to have minus 2 all over x plus 1, and we already have our c, so we don't need to write it. Now we have a couple common terms here. We have a 1 and 2 natural log of x plus 1, so we can rearrange that. So we can write this as 3 times the natural log of x plus 1 minus 2 all over x plus 1 plus c. And remember, that's the same answer as you had before using partial fraction decomposition. So keep in mind, there's not just one way to solve integrals. There actually can be, in theory, infinitely many variations and artistic ways of solving the same exact problem. So that's just a brief exposure on how to use partial fraction decomposition and how we can also use long division to solve integrals of rational functions. Hope you enjoyed this video, and I'll see you in the next one. Take care.